Hi class, this is the first part of our second lesson in Module 10, which is simple linear regression. To begin, let me take you back to something we did last time. To understand correlation, I created this example with 50 observations paired here, where I started off a random sample of size 50 from the normal distribution, mean 5, standard deviation 2. These were the x1 through x50. I created this error vector. This is standard normal distribution. Then the y1 through y50, well, I took 2x plus 3 plus the ith entry in the error vector. So this is a different plot than we saw in the notes last time, because every time you run this, you get a different x and a different error, and therefore a different vector y. But for this sample, the sample correlation coefficient is 0.9629158. This will be statistically significant. I don't have the core.test printed here, though. What I've added is this blue line, which looks like it fits the data pretty well. In fact, it should, based on how I created y out of vector x. So maybe I should write the blue line is a graph of y equals 2x plus 3. Slope 2 and intercept 3. Now let's move into simple linear regression. Suppose we have a random sample paired. We have x1, y1, x2, y2, out to xn, yn. The simple linear regression model assumes that yi is beta 0 plus beta 1 xi plus epsilon I, where epsilon I, this is our random noise. We've talked about this in previous lessons, and it's distributed as normal, mean 0, standard deviation sigma. Now, this beta 0 is the intercept, and beta 1 is the slope. There's really two viewpoints for statistical purposes. One would be that we assume x1 through xn are known, and we only consider the randomness from the noise, the epsilon 1 through epsilon n. Another viewpoint is we assume x1 through xn are random variables, but we make inferences on y conditional on the observed values of x. Either way you think about this, what matters is we are not making distributional assumptions on x1 through xn. We only assume that epsilon I, our random noise, is distributed as a normal random variable with mean 0 and standard deviation sigma. So as a recollection, the probability density function of this epsilon I would be this 1 over the square root of 2 pi times sigma, and then e to the minus epsilon I squared divided by 2 sigma squared. Now, what is the objective in regression analysis? We want to estimate the values of these parameters, beta 0 and beta 1. Now, note that if we know beta 0 and beta 1, we can predict y given an observed value x. So this is read the expected value of y is, well, we expect it to be beta 0 plus beta 1 x. You will also see this written as, say, mu y given x. But this is what we would predict y to be. At the same time, it's the mean of y given a specific x value. So that is, given an observed value of x, we expect or predict y to be this beta 0 plus beta 1 x. Now, let's talk about parameter estimates for a linear regression model. So starting on this page, following convention, I'll use lowercase letters to denote the actual observed values, x1, y1, out to xn, yn. So in the linear regression model, you see we can rewrite this epsilon I as yi minus beta 0 minus beta 1 x. And our assumption here is that this epsilon I is a normal random variable. Okay, let's take us back something to much earlier in the semester, which is likelihood. Well, we would just take the product. Here is the PDF for epsilon 1 times. Here is the PDF for epsilon 2 times. All the way out to here is the PDF for epsilon n. Epsilon 1 through epsilon n are independent here. And what I've done from this remark is I just replaced epsilon I with this yi minus beta 0 minus beta 1 xi. You will see that in all of these exponents. Now to maximize L, which is what we're interested in here, to find our beta 0 hat and beta 1 hat, these are MLE estimates, we can equivalently maximize the log likelihood. What would the log likelihood be here? And remember, when we're working with log likelihood, we have to use log properties. Okay, the first thing that I observe is all of these are the same and they're all multiplied. So really in L, I have this 2 pi sigma to the n. When I take the log of L, well, this will be minus n, let's write it, minus n log of the square root 2 pi times sigma. Now, what about the other term? So now I have products of n e to a powers. ln of e to a power is what's up in the exponent. Moreover, the product inside of a log will turn into a sum. So altogether, here's what we are going to have. We have 1 over 2 sigma squared. We have a sum, I equals 1 to n. Then the sum is what I see here, here, here. There's a negative. We have yi minus beta 0 minus beta 1 xi squared. Okay, here's the log of L. Now, I didn't write out the steps of all the log properties. I kind of talked about them and was able to realize what we get here, but you could work out the details if you're interested in doing so, writing them out. Now, remark, and this is an important part for moving forward. In order to maximize this function, the estimates, beta 0 and beta 1, well, where do they appear? Really in this sum. So we want this sum here to be as big as possible. This would say we want to minimize the sum without the minus sign in front. So I equals 1 to n of yi minus beta 0 minus beta 1 xi squared. Now, you notice what this is. So I'm going to work with this in just a moment, but don't you notice this is a sum, I equals 1 to n of epsilon I squared. So for the moment, this is really a comment, but this maximum likelihood estimates for beta 0 and beta 1 are called least squares estimates because they are minimizing this, the sum of the squares of the error terms. But I'll talk about that more in the next slides. Okay, so next page to find the MLE. Beta 0 hat and beta 1 hat, as I was mentioning, equivalently least squares estimates. What we want to do is simultaneously solve, well, we can take the partial derivative of this expression with respect to beta 0, set it equal to 0, the partial derivative of this expression with respect to beta 1, and set it equal to 0. So I'm going to color these two different things. Maybe I will call this green, and I will call this one orange, so we know which partial derivative we're working with. Let's work with the green one first. Now I'm not going to do the full calculation solving for beta 0 hat and beta 1 hat. I'm going to do part of it, and then you kind of can get the idea. You could finish it off if you're interested using some algebra. Let's take the partial derivative of this with respect to beta 0. Well, this will be a sum, I equals 1 to n. Remember, beta 0 is my variable. Okay, it's really chain rule. We take 2. Now we put in the entire inside function, yi minus beta 0 minus beta 1 xi, and then times the derivative of the inside function. Well, the derivative of this with respect to beta 0 is -1. So times -1. We set this equal to 0. Let's work with this further, and then we will do the orange one. So first of all, I have a 2 and a -1. I can factor out a -2. Also note that there is no square here. And so this is just a sum, I equals 1 to n. We have yi. Let me put some parentheses here. Then we have subtracted off a sum, I equals 1 to n of negative beta 0. But there is no I in this sum. So I have minus beta 0 n. That would be that sum. And then I have minus the sum I equals 1 to n of, let's see, I can factor out a beta 1. And we have xi. So all of this equals 0. I'm trying to solve for beta 0 and beta 1, hat, the minimizer. So I'm going to be putting hats on things in just a moment. But you notice we can just divide both sides of the equation by -2. Then we can move this to one side. I'm trying to solve for this. So here I'm going to come with some hats. Beta 0 hat times n will equal the sum I equals 1 to n of yi minus beta 1 hat times the sum I equals 1 to n of xi. Oh, we are in wonderful shape, because now to solve for beta 0, at least, we can just divide by n and make an important observation. We get that beta 0 hat will be, well, when you divide this by n, the sum of yi's over n, this is our sample mean of the y's. So we have y bar minus beta 1 hat times, now divide this by n. This will be the sample mean of the x's. Okay, so we have solved for beta 0. Now let's work with the orange one. So now, this is where I'm not going to do the full part of the calculations, but we will take the partial derivative with respect to beta 1, and I will mention what you do next. Okay, so when we take the partial derivative with respect to beta 1, we start off the same way. It's chain rule. Derivative of the outside, evaluated at the inside, times, well, now I'm differentiating with respect to beta 1, and so my derivative is minus xi. Minus xi. And we set this equal to 0. Okay, so at this point, I will give you guidance as to what comes next. We will substitute this beta 0 hat into this equation. And we can do some algebra to solve for the beta 1 hat. Okay, at this point, I'm going to move to the next page and show you at least one way to write the beta 1 hat. There are multiple equivalent ways of writing it. Okay, here we go. Ta-da! You can work through the algebra if you're interested, but here is beta 1 hat, and here was this beta 0 hat that we did in fact calculate. So I'd like to, by hand, do a very small artificial example, and we can make some sense of the calculations before we move forward. We have n equals 4 paired observations. Here are the x's. So let's add this up. What do we get? 4 over 4. We can see x bar is 1. And then the y's, 8, 3, 3, minus 2. Add these up, we get 14 minus 2, which is 12, divided by 4. So y bar is 3. Okay, so now we can calculate beta 1 hat first, then we can calculate beta 0 hat. Well, this is kind of a big calculation. For n equals 4, it's not too bad. So for I equals 1, in the denominator, you notice that xi is negative 1. So minus 1 squared. In my numerator, I have minus 1 times 8 minus 3. Okay, now we can do I equals 2. X is 0, so I have 1 squared. The y is 3. Oh, so I have 1 times 0. Very nice. Now for I equals 3. The x is 2, so I have 1 squared. And the y is 3. Oh, I have another 0. Okay, last one. For I equals 4, the x is 3. So I have 2 squared. And the y is minus 2. We have minus 5. Now, you see I mentioned it wouldn't be too bad when I equals 4. So you notice my numerator, I have minus 10, which is negative 20. In my denominator, I have 4 plus 1 plus 1 plus 4, which is 10. So I get negative 2. Next, once we have beta 1, beta 0 will be 3 minus 2 times 1. I just use this formula right here. What do I have? 5. Okay, so let's see, maybe I'll label these. This was our slope, and this beta 0 gives us our intercept. If we want, we could also write this expected value of y. This is given an x value, or the mean of y given x. This would be 5 minus 2x. Very nice. Okay, well, I just copied what we just calculated and said. So I want to make a chart just to make sense of this. Here are the actual observed yi's. And then we have this predicted yi, which is often we put a hat on it. This would be what's predicted by the linear regression model. Well, we just take this minus 1 and we evaluate. So we have 5 plus 2, which is 7. Here we evaluate. We have 5 minus 0, which is 5. Here we evaluate this. We have 5 minus 4, which is 1. And then we evaluate at 3. 5 minus 6 is negative 1. Now from this, we can also write down the error. This is the difference between the observed y and the predicted y. So if we have this plus this, it should equal the observed in this regression model. So here my error is 1, my error is negative 2, my error is positive 2. The last one, from minus 2, let's see, we would take minus 1. And then if you add these two, we get this number. Okay, great. Well, what I've plotted is these 4 data points and the pink line, slope minus 2 and intercept 5. Now I want to make sense of this column on my picture, and we can also reinforce why it's called least squares graphically. So we have these vertical bars. Note that everything in this second column actually falls on my line. This part, my predicted y's, they physically fall on my line. And then I have these vertical bars from the observed data points to this line. Well, how do we see this column? Okay, this length is 1. This length is -2. The negative is because the point sits below the line. This is 2, and this is -1. So the MLE, beta 0 hat and beta 1 hat, they minimize the sum of the squares of the vertical error bars in this picture. Really, it's the sum of the squares of our EI random noise. But if you've done least squares in linear algebra, where you calculate these things using matrices, it's the exact same thing. In fact, this example with the 4 data points, I've given in a linear algebra class on a homework assignment. We did not use these formulas from statistics, I will just say, but the least squares is exactly the same. A remark, there's one more parameter in this model, sigma, which is not of main interest. This is the standard deviation of our noise. We really only need it to judge how large the noise is, and we will typically use this estimator, this S squared. You might wonder why there's an N-2 in the denominator. It comes from degrees of freedom because we have 1, 2 parameters here. But in R, we fit a linear regression model using this LM. The good news is when we have a large data set, you are not going to be doing this by hand ever. So let me just show you the output of this linear model on this CATS data. So we've worked with this on a homework this semester. It's in the mass package. This CATS data contains heart weights and body weights for a sample of male and female adult cats. So the Y is the body weight. And the X is the heart weight. Maybe I'll make them capital and capital. Then I use this linear model function that we've used before. So it gives me this coefficients. What does this mean, or how can I interpret this? Well, this is the beta 0. Here is the beta 1. So what we get from this, the expected value of y given an x value, or the predicted value of y, would be here. Here's my intercept, and then plus 0.1603 x. In other words, this is the beta 0 hat, and this is the beta 1 hat, like this. Maybe I will just copy and paste this blue line is y equals times x. So we've talked about the linear regression model. We've talked about point estimates for beta 0 and beta 1. We used MLE. Equivalently, these are the least squares estimates. But what's coming next is statistical inferences in linear regression model. So we want hypothesis test really on this beta 1, the slope. This is the more important one. For hypothesis testing, we will have confidence intervals for beta 0 and beta 1, and well, many more things. So this is to come in part 2 of this lesson. Thank you so much.